Without motion, most machines might as well be paperweights. Lucky for us, there's all sorts of mechanical tricks employable in the pursuit of motion. All we have to do is pick the right one. Let me explain. This is my bandsaw, but it hasn't always looked like this. In an effort to streamline the task of trimming, cutting, and generally docking raw material, I decided to manufacture a motion platform of my own design. And while the platform portion of the pursuit was fairly simple, the motion component quickly became far from it. Really don't know what I'm going to do. But before I try to explain all of this, there's a few things you should probably know. First of all, the motion component I mentioned is fairly straightforward, by which I mean all we're really trying to do is push the saw forward along the straight line defined by its linear guides. But while other machines might rely on rigid positional control through some kind of lead screw or gearbox, the bandsaw is much more worried about how much force is behind the cut. Press too hard, and the blade starts to wander, bind, and make expensive noises. But if you're too gentle about it, the teeth start rubbing and create heat instead of chips. Now, all sorts of things influence this ideal chip load. From tooth count to material thickness, to the phase of the moon. The point is, a bandsaw feed mechanism requires some amount of compliance that a purely mechanical drive would struggle to provide. So I chose a pneumatic approach. I figured it'd be easy enough to set the force with a regulator, and I should be able to moderate speed with a flow control valve. Oh, and in case there's any doubt in your mind, this is absolutely foreshadowing. Aside from the abundance of headaches I'd yet to encounter, there was still the question of how I was going to transfer the force from the actuator to the carriage carrying the saw. Made a little more complex than strictly necessary by my insistence on mounting it entirely within the footprint of the existing table. Which is exactly the kind of problem Onshape is built to solve. And with their latest model-based definition update, you can embed dimensions, tolerances, and notes directly into the 3D model, which handily removes at least one opportunity for me to get things wrong. Click the link below to try Onshape Professional free for up to 6 months. Now you might be aware of this, but basically all pneumatic cylinders have this annoying tendency to more or less double in length when actuated. So, determined to avoid the unsightly addition of a 500mm tube protruding somewhere from the machine, I knew I'd need to get a little clever. I found more than one dead end in my search for a motion doubling mechanism to fit neatly between the carriage and its actuator. But putting aside chains, cables, and superconducting hypertransducers, I finally arrived at the obvious conclusion. The rack and pinion, or to put it more accurately, the rack and pinion. As complicated as that might seem, it's pretty easy to understand once you see it in action. But first, we'll have to whip up a couple of parts. The first piece has a pretty basic form, for an equally simple function of spacing the dynamic rack out from the carriage. But it's often the simplest looking parts that create the biggest work-holding challenges. And having completely botched the sketch I gave to the laser cutters, I'd have to overcome those challenges, all on my own. The brand spanking bandsaw table, though still incapable of moving under its own steam, was already proving its worth, making quick work of the bulk stock to be removed. See, the issue with this part stems from the long, thin, stem-like section, in combination with the incredibly tasteful radii present along its profile. I could spend hours on the subject of why this particular part is a pain in the ass to hold onto, but it should suffice to say that any of the clamps in my collection would sit squarely in the way of the toolpaths necessary to effect its final form. The solution here was borrowed from the 5-axis world, and consisted simply of some extra stock and a healthy overhang, providing unrestricted access to all but a single face. Once profiled and chamfered, I could make use of the bandsaw again, to separate the part from the pile, before cleaning up the final face on the manual milling machine. Any human error at this stage of a one-off would spell heartbreak, so I let the machine counter all the bores and drill all the holes. with the notable exception of these two. With an aspect ratio approaching 12 times drill diameter, the main mounting holes would be as sketchy to drill as they were critical to the function of the part. So to ensure alignment and avoid an embedded tool-related do-over, I only computer numerically spotted the ends of each hole, reserving their union for a setup more focused on the human touch. With all the holes tapped, I finally had amenity for rack and rack, but pinion and pinion still had no place to go. Tackling the carriage that would carry those pinions involved a similar excess stock work holding strategy. But the tool holding strategy was rather unique. Strictly speaking, it wasn't much of a tool holding strategy at all. Fuck. And the admittedly spirited roughing cuts were all the encouragement this 10mm end mill needed to take a trip right through the machine's table.
Talk about a fucking apprentice, Mark.
I never much liked pulling out, but misery builds character, and I've got to build this bandsaw. Dialing back the step over did the trick, and the remainder of the machining went by without a hitch. I now almost had a place for these pinions to go, but I'd first need a bushing or two to take up the slack between each locating boss and its pinion bore. Bronze is probably overkill for this, considering my plan to print the pinions in a fairly slippery polymer. But there's a chance that one day I'll have some steel blanks, a set of M2.5 gear cutters, and literally nothing else to do, in which case I'll be very glad to have used an appropriate bushing material. By this point, I had a growing collection of moving parts that would very much like to be enclosed, which meant covers, which meant sheet metal. But while the prospect of an afternoon of gear cutting is almost pleasant, there's nothing worse than sheet metal work in a non-sheet metal workshop.
What is it with me and holes in sheet metal?
Which is where the sponsor of today's video, PCBWay, comes in. Aside from being a leading manufacturer of custom printed circuit boards, PCBWay offers a comprehensive range of CNC manufacturing services, from 3, 4 and 5 axis milling and turning, to 3D printing, to laser cutting and sheet metal bending. So instead of fighting a flat piece of metal for an entire afternoon, all I had to do was upload my design and tick a few boxes. We'll get these covers installed a little later on, but for now, if you'd prefer to skip the sheet metal phase entirely, check out PCBWay using the link below. With both brackets complete and all the toothy bits printed, it was finally time for a little assembly. First thing first, a 12mm linear guide rail fits neatly to the frame, held in place with a few M3 fasteners. Then, the pinion carriage can take its place atop the two bearing blocks before the pinions and their bushings are bolted on. With the pinions in position, I can add the fixed rack, adjusting for the perfect amount of mesh. And prior to attaching its dynamic counterpart, I'll first install the second bracket, and then the final piece can fall into place. Now there's no denying the visual appeal of this assembly, and the manner in which it addresses the issue of cylinder length to available space ratio should be almost apparent. But just in case it hasn't quite clicked, let's take a closer look. The simplest way to understand gears is to think of them as a bunch of levers arranged in a circle. Each tooth basically acts like a tiny lever arm, pushing on the opposing tooth at a fixed and equal distance from the center. So if we hold one end of that lever still, any motion applied to its central pivot causes the opposite end to travel twice as far. In our practical application, the static rack serves as the fixed end of the lever. The moving rack becomes the output, and the pinion is both the central pivot and input, neatly doubling motion and halving the length of the actuator required to get things moving. The addition of a second pinion allows the dynamic rack to be shortened and, in operation, pass between the two. But without an actuator, it's all fairly pointless. So let's talk pneumatics. There's a number of challenges involved in integrating pneumatics into a system like this. The first and arguably most common of which occurs when ordering components. Now, it's not my first rodeo, so I'm pleased to report I've finally figured out that a 1/4-inch pneumatic fitting has a 1/2-inch thread OD.
Someone make this make sense.
But that didn't stop me from ordering the wrong pneumatic cylinder.
That's too fucking big.
Twice.
That's too fucking small.
Well, the second time it wasn't my fault. But it still meant another fortnight of crossed fingers, waiting for a parcel that might have the part I designed the whole machine around. Fortunately, being neither too long nor too short, The third cylinder was just right, which meant it was time to run headfirst into the next obstacle, namely the fact that a solely pneumatic system is completely unsuitable for the task at hand. See, air is, well, compressible, kind of like a spring. So even though we can regulate the force behind the spring, any force applied in front of it, like say the resistance from a cut, is going to cause some amount of compression. And as soon as that force is removed, as we might expect to happen at the end of a cut, it'll bounce straight back and rocket the saw right into the stratosphere. You can limit the delta V a little by restricting the flow of air out the other end of the cylinder, but I can confidently say that that really doesn't work as well as it sounds like it should. Now, I can't say I wasn't warned about this one, but all I can offer in the way of an explanation for completely ignoring those warnings is that sometimes you just have to learn things the hard way. But I wasn't ready to give up on the pursuit of a smooth, controlled application of linear force, and my lesson in fluid mechanics had only just begun. I know filling a pneumatic cylinder with oil feels wrong, but desperate times call for damping measures, of a kind only a non-compressible fluid can provide. My first experiment involved the addition of a secondary 16mm cylinder, filled to the brim with the finest surplus 4-stroke motor oil I could find in my cabinet, and sealed up with a tube between its two ports.
Why is it all squishy?
Frustratingly, even a small amount of air trapped in the system is enough to interrupt the cylinder's otherwise perfectly smooth and controlled stroke.
Feels pretty good, except for right here.
Bleeding the air from the system was a bit of a pain, but worth it in the end, if only to remind me that there's less space on the rod side of a cylinder, and the extra oil opposing it has to go somewhere. I'm sure I could have spent half an hour brushing up on the fundamentals of hydraulic control theory, but several days of messing around with cylinders and reservoirs and valves and regulators ultimately led me to the same conclusion of a dual-acting air-over-oil cylinder system that mostly doesn't leak. Here's how it works. The main cylinder, mounted between the table and pinion carriage, has its rod end connected to the blind end of the slightly shorter cylinder I received by mistake, creating a closed hydraulic circuit which I could then fill with oil. The line connecting the two includes a couple of throttle check valves, back to back and in series, allowing the flow to be metered independently in each direction. The power delivery necessary to extend the main cylinder still comes from an air supply, but the addition of our oil circuit means any movement of the main piston displaces oil through the connecting line, its flow metered by the throttle valves, into the second cylinder. Retraction follows the same principle, but with air supplied to the secondary cylinder, and the end result is smooth, consistent, and controlled motion in both directions. As happy as I was to have reinvented the wheel, I'm still not totally thrilled with the packaging. But for now, it moves more than well enough to move on to more pressing concerns. There's not a whole lot to say about the fences, other than I didn't have a lot of time to think about their design.
Alright, let's see how we did.
And even less patience when it came time to make them.
It's definitely tilting back a little bit.
But what I lack in all other areas, I'm starting to make up for in machine tools. And a quick skim with the fly cutter was all it took to square things up.
Okie dokie. Beautiful. Looks great.
Which means I can finally demonstrate what all the bandsaw moving on a track fuss is about.
Bandsaws. Despite its mechanical simplicity, or perhaps because of it, there's no denying the utility of the metal-cutting bandsaw to the subtractive machine.
Not as easy as it looks.
I never said it was. The bandsaw. Despite its mechanical simplicity, or perhaps because of it, there's no denying the utility of the metal-cutting bandsaw to the subtractive machinist.